Just moments ago, a revolutionary telescope was launched into space, marking the beginning of a new era of scientific exploration.
James Webb Space Telescope just revealed the true scale of the universe by capturing light from galaxies that existed only a few 100 million years after the Big Bang, stretching our understanding of cosmic history from what was once imaginable to an almost unfathomable expanse. The moment unfolded as an orchestration of science, technology, and human aspiration, a symphony of precision unfolding 1.5 million kilometers from Earth at the Sun-Earth L2 point, where the observatory's golden mirror, spanning 6.5 meters in diameter, gathered faint whispers of ancient starlight. This marvel of engineering, cooled to near absolute zero to detect faint infrared signals, revealed an orchestration of cosmic evolution that reshapes not only astrophysical theory, but also the very way we perceive our place in the cosmos. The data streamed back to mission control, and as astronomers processed terabytes of information, it became clear that the images bore testament to an era when the universe was a fraction of its current age, hosting structures that challenged prevailing models and invited deeper reflection on the intricacy of cosmic evolution. Before we start, smash the like and subscribe buttons for more updates. The unveiling of the deep field images depended on Webb's unparalleled sensitivity to infrared wavelengths, a window into epochs obscured by intervening dust and the redshift of light from the earliest stars. In contrast to its predecessor, the Hubble Space Telescope, Webb illuminated the invisible, peeling back curtains to reveal galaxies that had remained elusive for over 2 decades of astronomical inquiry. Each pixel in the mosaic of these images corresponded to a time capsule, a record of photon journeys spanning nearly 13.5 billion years. As each faint smudge of light resolved into a distinct galactic structure, some with orderly spiral arms, others chaotic assemblages of nascent stars, astronomers recognized that the empirical foundation for understanding cosmic dawn would need revisiting. These images, brimming with thousands of galaxies in a single field of view, underscored a universe far richer and more varied than theoretical predictions had allowed. Observers noted clusters forming earlier and more intricately than expected, raising profound questions about how the initial seeds of structure grew so rapidly in the aftermath of the cosmic dark ages. Prior to this revelation, prevailing cosmological models painted a coherent, if incomplete, picture of how matter agglomerated under the influence of gravity, forming the cosmic web that structures galaxies into clusters and filaments. Yet Webb's observations revealed that some galaxies boasted mature stellar populations mere hundreds of millions of years after the Big Bang, implying that star formation rates in the early universe had been extraordinarily efficient. This suggested that the interplay of dark matter halos and baryonic matter was more nuanced than existing simulations coded into supercomputers could replicate. Models had assumed certain thresholds for cooling mechanisms, metallicity evolution, and feedback from supernovae. Yet the early appearance of massive galaxies implied that star-forming regions coalesced and cooled far more quickly than those frameworks allowed. The revelation compelled theorists to re-examine assumptions about primordial gas chemistry, the role of molecular hydrogen cooling, and the timeline for the first generation of stars to seed their environments with heavier elements. It became evident that the earliest chapters of cosmic evolution, long hidden from human sight, had progressed with a sophistication that challenged our most fundamental assumptions. Beyond the astrophysical particulars, Webb's deep field observations reframed fundamental inquiries into dark matter and dark energy, the two invisible components that together comprise over 90% of the universe's energy budget. By mapping the distribution of galaxies at various redshifts, the telescope provided empirical anchors for refining measurements of cosmic expansion and elucidating how dark energy's influence evolved over time. The clustering of galaxies in the deep field, a tapestry of galactic congregations against the backdrop of cosmic voids, yielded new constraints on how dark matter halos grew and how dark energy's repulsive force influenced large-scale structure. The subtle gravitational lensing observed in the data, where light from background galaxies is bent by foreground mass concentrations, offered a novel way to chart the unseen distribution of dark matter. These insights allowed researchers to better calibrate the universe's expansion rate, a parameter that underpins estimates of cosmic age and fate. Through this lens, The images were not just aesthetic marvels, but diagnostic tools, unveiling how the unseen scaffolding of dark matter shaped the universe's history from its earliest phases. The technological prowess that enabled this breakthrough depended on a succession of innovations. From the perfection of beryllium mirror segments polished to atomic smoothness, to the deployment of a 5-layer sunshield the size of a tennis court. The sunshield's precise engineering maintained Webb's instruments at cryogenic temperatures, minimizing thermal noise that could obscure faint infrared signals. These design triumphs, decades in the making, represented a global collaboration of space agencies, academic researchers, and industry partners. Behind every pixel lay mountains of calibration data, algorithms tuned to subtract cosmic rays, stray light, and instrument artifacts. The meticulous efforts of ground teams to refine data pipelines and correct for distortions were as essential to the revelation as the telescope's optics themselves. In the weeks leading to the public release, engineers and scientists collaborated around the clock to ensure the integrity of information, verifying that the light curves and spectra would withstand scrutiny. Thus, when the first deep field mosaics appeared, they symbolized not just cosmic truth, but also the culmination of human ingenuity triumphing over the challenges of observing the farthest reaches of time and space. The emotional resonance of witnessing galaxies from the cosmic dawn cannot be understated. For centuries, humanity's gaze extended no further than our own Milky Way, then reached modestly into nearby galaxies, and finally saw out to cosmic horizons with telescopes like Hubble. Webb's deep field turbocharged this progression, transporting observers to a vista where the universe, in its infancy, displayed a riot of galactic forms and interactions. For the first time, scientists looked upon stellar nurseries where population 3 stars, the first generation of stars formed from pristine hydrogen and helium, may have existed, leaving spectroscopic fingerprints in the infrared that could confirm their existence. The faint glows hinted at chemical compositions unmarred by heavier elements, offering a glimpse into the primordial alchemy that forged the first atoms beyond hydrogen and helium. These glimpses invited a visceral appreciation for how matter evolved from simplicity to complexity, how cosmic chemistry progressed to create the building blocks of planets' life and intelligence. In that instant, the palpable thrill among researchers and the broader public alike reaffirmed that exploration of the cosmos remains an endeavor as much about wonder as about data. Contemplating the images led to philosophical reflection on cosmic scale and human insignificance. The depth of the field, a tiny patch of sky roughly the size of a grain of sand held at arm's length, encompassed thousands of galaxies, each teeming with billions of stars. Extrapolated across the entire sky, estimates of the number of galaxies ballooned, hinting that the cosmic ledger held trillions of potential stellar systems. The notion that each pinprick of light represented billions of suns, many orbited by planets, suggested that the conditions for life might exist elsewhere in profusion we have yet to imagine. Yet the diversity of galactic forms, compact ellipticals, sprawling spiral arms, irregular clumps, underscored that cosmic environments could vary tremendously. Some galaxies appeared to be forging stars at staggering rates, while others showed signs of quiescence. Such variety implied that the evolutionary pathways for galaxies, and by extension for potential planetary systems, were manifold. In this tapestry, humanity's own spiral home, the Milky Way, seemed at once familiar and extraordinary. A pattern recurring throughout the cosmos, yet also one distinct in its own cosmic neighborhood. The telescope's spectroscopic capabilities took center stage alongside its imaging prowess. By dispersing incoming light into constituent wavelengths, spectrographs aboard Webb could decode the chemical makeup, temperature, and motion of celestial objects. Observations of early galaxies revealed emission lines from ionized hydrogen, oxygen, and carbon, unlocking clues about how quickly these galaxies converted gas into stars. Measurements of metallicity, the abundance of elements heavier than helium, helped trace how successive generations of stars enriched interstellar mediums over time. Through these spectral fingerprints, astronomers could deduce that some early galaxies had already undergone rapid chemical enrichment despite their youth, implying that supernovae and stellar winds had recycled matter with remarkable alacrity. Such findings hinted at feedback mechanisms, processes by which stars affect their surroundings, operating more violently or efficiently than previously surmised. As spectroscopic data accumulated, models of star formation and galactic evolution required recalibration, weaving a more intricate narrative of how the first cosmic structures transitioned from diffuse gas clouds to stellar metropolises. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the James Webb revealing the universe's true scale? We want to hear from you. Thank you for watching, and see you next time.